Okay, so in terms of our extensive forms, we've talked about Nash equilibrium, we've talked about solving games backwards, and now let's talk about subgame perfect equilibrium. So subgame perfection was a concept that was defined by John Harsanyi, and it gives us a way of solving extensive form games. And in particular, it's going to coincide with the backward induction solution in games of perfect information, but it's also going to provide for predictions outside of that, and we'll get to that later in the course. But it also works in a different way than backward induction. So backward induction will be a way of finding subgame perfect equilibria in games of perfect information, but more generally, subgame perfection is a different way of defining that. So in particular, what we first have to do is define what it means to talk about subgames. So what's a subgame? So in games of perfect information, a proper subgame is going to be the entire game. So we'll have a definition of proper subgame here being the entire game that remains starting from any non-terminal node. So we look at a node that's not a terminal node, and if we start a game from that point onwards, then we have what's called a subgame. So if we look back at our example of the entry game, we could start at the node where player 2 is making a decision of fight and accommodate, and if we cut the game off at that point, so we chop the game here, then what remains down here, ignoring the first choice of the first player, is a proper subgame. Right? So this looks like a game in its entirety. We can think of this as an extensive form on its own, and then solve that and make predictions about what's going on here. So that's one subgame here. Another subgame in this is the entire game. So this is also a subgame, right? We start at this node, and it includes all the game that follows the node where player 1 moves. So this is another subgame. What's not a subgame? What's not a subgame is say taking part of the game where the first player moves and then includes, say, a node down here, but not include what follows after player 2 moves. So we can't chop a game and chop parts of it off. Once we start at a given node, we have to include everything that follows that in order to be a subgame. Right? So this does not include all the nodes that are preceded by node 1. So we're losing the terminal nodes down here, and that's not a proper subgame. Okay. So in general, the subgame is the entire remaining game from some non-terminal node that has a singleton information set. So with the definition of subgame in hand, then we can define what's known as subgame perfection, or also known as subgame perfect equilibrium. So also subgame perfect equilibrium. And what is it? It's a specification of strategies that form a Nash equilibrium in every proper subgame, including the original game itself. So it has to be not only a Nash equilibrium from the beginning, right? So it includes the idea that it has to be a Nash equilibrium overall, but it also has to look like a Nash equilibrium from all further points that are entire subgames. And in particular, even at points that might not be reached in the tree, it has to be an equilibrium. So we have to prescribe that people play as if it's an equilibrium in from every possible node onwards in a game of perfect information. So for instance, if we go back to our entry game, then the specification of strategies to be a subgame perfect equilibrium have to be a Nash equilibrium in each proper subgame, so that includes this subgame down here. So if we look at that subgame, there's only one Nash equilibrium in this lower subgame, right? So this is just a one-player game, but in terms of their choices, they either choose to fight or accommodate. They either get a payoff of 0 or pi. Pi is bigger than 0, so the only solution that is going to be a Nash equilibrium in this subgame is to accommodate. So if we want to specify a subgame perfect equilibrium, it's going to have a specification of player 2's strategy be accommodate in the subgame. Then marching along back up the tree, in the larger subgame, given that we have a specification of strategies that are Nash in this subgame, then we're looking at something which is accommodate. So something which is a Nash equilibrium of the overall game, given that we have to have accommodate in this subgame, the only possible equilibrium then is for firm 1 to enter. So we're getting exactly what we got out of the backward induction solution, but here from a definition which just says we require things to be Nash in every proper subgame. If we go back and look at the other Nash equilibrium that other pure strategy Nash equilibrium that we solved for earlier in this game, the one where firm 1 stays out because it anticipates that firm 2 is going to fight, this is not a subgame perfect equilibrium. Why is it not a subgame perfect equilibrium? Because when we look at the subgame, the specification of fight is not a Nash equilibrium. So it fails the requirement that the play be a Nash equilibrium in every possible subgame. Right? So it's not an equilibrium, and it's not an equilibrium in the subgame that follows entry, even though that is never reached as part of the equilibrium. So Nash equilibrium allows this strategy to be played because it's never actually reached, but subgame perfect says even if it's not reached, it still has to be a Nash equilibrium at that point onwards. And that extra requirement rules this out as a possibility and then rules out this as an equilibrium altogether. Okay, so what do we know about games of perfect information and subgame perfect equilibrium? Well, some nice things are true. First of all, the set of subgame perfect equilibria coincide with those found via backward induction. So if you run the backward induction algorithm, that's a way of locating the subgame perfect equilibria in games of perfect information. If the payoffs are distinct across terminal nodes so that players are never indifferent, then there's a unique subgame perfect equilibrium, and that's found by the unique backward induction solution in that case. And more generally, the set of subgame perfect equilibria are always a subset of the set of Nash equilibria. And in some games, for instance, the one we just saw, it's a strict subset. So sometimes it could be that they coincide, but in some games it'll turn out that they're a strict subset, as we just saw in the previous example.